Good morning, everyone. We just start our today's class. In today's class, we just discuss about the Fermi level. Right. In the previous class, we had an expression regarding the density of electrons in the conduction band. So, in the next class, we'll go for the expression for density of holes in the valence band. So, before that, what we do is that again we just go for the Fermi level. Actually, in the previous class we discussed about the density of energy states, and also we just discussed about the Fermi level, Fermi function. So from where actually it has been coming. So that particular aspect that today's class will deal with this. So the Fermi level is nothing but the electrons in a solid obey the Fermi Dirac statistics, right? So any electron in solid is obeying the Fermi Dirac statistics. This is a statistics which is given by two scientists. So that is Fermi and Dirac. So it has been named under them. So electrons in solids obey Fermi Dirac statistics, and what they assume in this particular statistics is that. So what is that consideration? You can just see this PPT where you will find that. See in the PPT it has been very clear to you. So these aspects we just discussed in the previous classes. So here in our today's class, we just start with the Fermi level. Some students may have some problem with this. So we just discuss this again. What is actually the Fermi level and what is actually PN junction diode? Then again we'll go for this. What you can say carrier concentration in the holes, right? So that will be, I think that will, you'll feel comfortable when you go for this, right? Now, so electrons in the solids will obey the Fermi Dirac statistics. So the following consideration in these statistics for the see when I say Fermi level, so what is the need of studying this Fermi? See, when you talk about electrons come under the category of fermions. We'll call the electrons are fermions, and you already know that they are the elementary particles which cannot be seen with our naked eye. So therefore, for mathematical expression, for mathematical calculation purpose, we'll use the what you can say of the probability concept. And in that probability concept, what we are doing here is that we are using the integration and we are calculating the carrier density of the electrons and the holes, right? So the carrier concentration of electrons have been calculated in the last class. Again, just for your convenience, we are just repeating this, what is actually the Fermi level. So in the previous class, we just discussed about the diagram where we have written EF, right? So EF is nothing but Fermi level, right? So again, I will just go in detail about this Fermi level in today's class. So electrons in the solids obey the Fermi Dirac statistics. So the following considerations are used in the development of this statistics. So in this, when you go for this statistics, so there will be the particles. If you talk about electrons, right? So the fermions, the electrons will come under the category of fermions. So they are called indistinguishability of the electrons. The first consideration what they have done is that you cannot distinguish the electrons. So electrons in the Fermi Dirac statistics obeys the special character that is called wave nature. So electron here it is behaving as a wave, and also it obeys the Pauli exclusion principle. So what is this Pauli exclusion principle? No two electrons will have the same set of quantum numbers, right? So that is called Pauli exclusion principle. And f of e is given by mathematically 1 by 1 plus exponential of e minus ef by k into t, where k is Boltzmann constant and capital T is the absolute temperature. Here you can just see what is k. K is given by 8.6 to 10 into 10 power of minus 5 electron volt per Kelvin, and that can also be written as in terms of joules, 1.38 into 10 power of minus 23 joules per Kelvin, right? The function f of e. Now this function f of e is called Fermi Dirac distribution function. We say that this is called Fermi Dirac distribution functions, which actually gives the probability that what is that? So this mathematical expression is all about. It will give us the probability of the available energy such that the energy which is occupied by the electron at some absolute temperature, and this quantity EF is known as Fermi level, and it is a very important or significant quantity with respect to the semiconducting behavior. So for an energy E is equal to EF, the occupation probability will is given by, so see, if E value is equal to EF, then if I substitute here E as EF, so what it will be? E is equal to EF. So EF, if I substitute it, so f of EF is equal to, see, instead of E, what I'm doing is that I'm just substituting E as EF. So wherever we find E here, we are just substituting with EF. So what you will ultimately get? Exponential of 0 by kt to the power of minus 1. So this will give you the value as 1. This exponential EF minus EF by kBt will become 1. So 1 by 1 plus 1, that is equal to half. This is the probability of electron to occupy the Fermi level. We want the Fermi level value. So what is the probability of the electron will occupy the Fermi level? It is half. So by mathematical expression, we can conclude that the electron here will behave as there is a probability that electron may be available at the Fermi level. There is half hour, 50% there are chances of having the electron at the Fermi level. Now this is the reason that we have used the f of E value in calculating the carrier concentration of intrinsic semiconductor, where we had derived the Z n E is equal to Z of integration of minimum energy to the maximum energy, Z of E into F of E into dE. So Z of E we already discussed, pi by 2 8 me asterisk by h square whole to the power of 3 by 2 into e to the power of 1 by 2 the E, right? So now we're right. So this is actually, what is this Fermi Dirac distribution function? What is happening to the Fermi Dirac distribution function at different temperature? Here we need to remember that when we talk about temperature, so is there any dependency of temperature on the distribution of electron? So what happen if I increase the temperature? What happen if I decrease the temperature? That particular aspect we are studying in this particular slide. So what is happening is that exactly at 0 Kelvin, when there is a 0 Kelvin, you will find that the available energy will be filled up to EF. So with electrons, so we just discussed in the last class what is actually EF. So at EF, all the states above EF are empty. Now at the temperature, when you increase the temperature higher than 0 Kelvin, there is some probability of existing the electron. The Fermi level is be filled, and the electron, there is a corresponding 1 minus f of E that is that says that below EF everything is empty. So if the temperature is 0 Kelvin, then that particular EF value, so above the EF you'll get all the things empty, and if the temperature is raised above 0 Kelvin, so what will happen? You'll get the 1 minus f of E value, that is below EF. You'll find that there are empty energy state. You can just see this particular shape, this square shape, you can just see. So at 0 Kelvin you will obtain this particular aspect, where E is the energy of the electron, and here f of is the Fermi function. So this is half probability, and this is the maximum probability of getting the electron. So now, so this is the temperature higher than some probability of electron is there. So the Fermi function is symmetrical about EF for all the temperatures. So you can just see this Fermi function. See, electron hole concentration at equilibrium. So the Fermi distribution function can be used to calculate. Just now we had just calculated the concentration of the electrons and holes in the semiconductors. That is called if the density of the available energy states in the valence band and the conduction band can be calculated. So the concentration of the electrons in the conduction band, I said to you that n suffix here O, so you can just write n suffix E also. So what is the minimum value? EC to infinity f of E, so into ZE, or you can write here in E, that is, see here I can just see this is you can write ZE or NE, that is only the indication part, right? So where Z of E or N of E, dE is the density of energy state. So in the energy range, this is the range of energy. So dE will give us the range of energy. Now the subscript 0 is used for the electron and hole concentration, and if instead of that you can write N naught P naught. So if it is Ne also, there is no problem. N naught is also no problem. So now the number of electrons per unit volume in the energy range is the product of, see, if you want to calculate the number of electrons, right, which will be the product of density of energy state and the probability of occupancy. That is called Fermi function. Thus, the total electron concentration is the integral over the entire conduction band, and this can be calculated by using the quantum mechanics, and we'll discuss about the quantum mechanics in the later unit. So, where Z of E or N of E is proportional to e to the power of 1 by 2. So, now this is the case of the value that we have already calculated in the last class. Now, we are not going for that. Why? Because we are just calculated that. So, now we'll just start up this next important aspect. So now, right. See, what is actually PN junction? Now, we just discuss about pure semiconductor. In this class, we just discuss about what is actually the meaning of p-type and n-type semiconductor. Here, when I join this, see, just now we concluded about intrinsic semiconductor. Now we are interested in studying about p-type semiconductor and n-type semiconductor. What will happen if I join the p-type semiconductor and n-type semiconductor? I can get a junction. We'll call, see here, just see this N and P. So what it indicates, now we want to talk about extrinsic semiconductor. So the interface separating region between N and P or P and N, so region, this is actually called as the metallurgical junction. This boundary, we're talking about this boundary, right? This is called metallurgical junction. For very simple aspect, we'll just go for very simplicity, we'll consider this as a particular function, step function, right, which will tell us the distribution. Here you can just see N and P, there is a uniform distribution, right. So initially there is a very large density. You find that here we can just see this figure Na and Nd. Why I have written here Na and Nd? Here Na and Nd indicates that this aspect is completely, we talk about acceptor impurity and donator. Here we have donor impurity. Here in the P type you will have a acceptance. So acceptance impurity is given by Na, and donor one is given by Nd. That is called N. So now, so here initially there will be very large density in between the electron and hole concentration. Majority, you know that majority carrier in the in N region, the majority. See, whenever I talk about semiconductor, there are two charge carriers, electrons and holes. So if I talk about n-type semiconductor, definitely you'll have more number of electrons. So more, if you possess more number of electron, I will just say that that particular electrons are nothing but majority charge carriers. So what is a majority charge carrier? Electron. So the majority charge carriers, electrons in the n region, will start to diffuse into the p region. They will be attracted with the positive holes. So they want to diffuse from here to here. So here you can see majority electrons in the n region will begin to diffuse into the p region, and the majority carrier holes in the, here P, what all the majority charge carriers? Holes, and minority charge carriers? Electrons. Here the majority charge carriers are electrons and minority charge carriers are holes. So here, when majority carrier electrons in the n region will begin diffusing into the p region, and the majority carrier holes in the p region will begin diffusing into an n region. If we assume that there are no external connections, if you don't give any connection to it, to a semiconductor, then the diffusion process cannot continue. So see, some of the electron will diffuse into the p region, and some of the holes from p to diffuse, from p to travel or move to diffuse in the n region. So now, in order to understand what is actually this, I say that diffusion, right? So what is actually the diffusion is all about? You can see, let us assume that we have two boxes, right? So in order to understand very clearly what is actually the meaning of diffusion, so what we have done is that we have taken two boxes here. One contains red air molecules, another box is containing some blue molecules. So now this is a type of, you can just say this is type of pollutants, right? Pollutants. So let us, if I just join this particular two boxes, and if I remove this particular wall, right? This is the wall, right? When you join something, definitely you will form a layer. When you join something, you find a layer, and here when you join the layer, so each type of molecule start to move from the region from low concentration to the, due to the concentration. See, you can see, if I just remove this particular wall, so each time of molecules start to move to the region of their low concentration to the concentration gradient here. They have been mixed here. If I remove this, right? So what is happening? So each type of molecule start to move to the region of the lower concentration. So eventually there will be homogeneous mixture. You can find this. There is a homogeneous mixture of two types of molecules. So here one type of molecule is the red air molecules. Here you'll find blue air molecules, and this is homogeneous mixing of the molecules, right? So this is the way that how the transfer of we can say the, instead of the pollutants we say that electrons and the holes, right? So now, so what is actually p-n junction? See, so in the lower classes you just studied about p-n junction. Here we try to again repeat the same thing with a broader aspect, in the broader aspect. So which cannot the see we just consider the p-n junction. You can just see, if I talk about p-type semiconductor, n-type semiconductor, and definitely if I join the two types of semiconductors, extrinsic semiconductor, a junction is formed. So now, because of this, what you can say, see, as the electron is diffusing from N, you see, from the N region, the electrons are diffusing, right? And positively charged donor atoms are left behind. See, they are diffusing from N region, electrons are diffusing, and what is remaining here? Some positive charges are remaining here, right? That is called holes. Now, holes are diffusing from P region. Holes are diffusing from P region, and they uncover the negative charge. You find the negatively charged here, and these holes are diffusing to the other level, and this is called minority carriers in the N region. Right? The net positive, you find that the net positive and negative charges in N, you can see in N region you got a positive charges, net positive charge, and in the P region you got a net negative charge. So the net positive and the negative charges in the N and P regions therefore develop an electricity. When I say electric field, definitely you'll have a positive charges and negative charges. So there is a formation of a junction, right? At the junction there is formation of positive and negative charges. Now you can see the net positive and the negative charges regions as we have shown to you. So now this is called space charge region. We'll call this is called space charge region. The net positive and the negative charges which is formed, we'll just say that that is called space charge region. Essentially all the electrons and the holes are moving will move towards this space charge region by the electric field. Since the space charge region is depleted, so they are not moving. What is the meaning of this? They are not exactly moving now, so they are not moving. So you require some external field. So where, see the region where, see you can just see negative charge is there, and here you find a positive charges. They are not moving. So we will call this as space charge region. Now see this region is known as depletion region, where the region in which the majority charge carriers are depleted. Depleted means they are not supposed to move from that particular position. They are not moving. They are not moving. They are moving. They are leaving. They are being in stagnant position. So now this is this particular region, where this region is known as depletion region. So the space we call depletion region as also the referred to as space charge regions, right? The net positive negative charge ions there where the region where the majority charge carriers are depleted. So you can just see this, the electric field in the space charge region produces another force on the electrons and holes, which is opposite to the diffusion forces of each type of material. And at thermal equilibrium, the diffusion. So what did this mean? See, and I'm just not reading it. So for your convenience, actually, I want to tell you that this region is known as depletion region. So as it is, I'm trying to tell you that the region where the majority charge carriers are depleted, so we'll call that region as the depletion region. Now, what is actually the p-n junction? You can just see this is a conduction band in terms of band. See, if we talk about band, I just now in the last class I told you that whenever we talk about junctions, so whenever we talk about semiconductor, we'll talk in terms of the bands. So the junction is in, now the junction is in thermal equilibrium. You can just see this is Ec, this is Fermi level, this is the Ev, E suffix V, energy of the valence band, energy of the conduction band. This is right energy. What is this? This is the Fermi level. Exactly, EF is the Fermi level. Now the junction is in thermal. We say that this is the Fermi energy level is constant throughout the entire system at thermal equilibrium. When you don't apply any amount of external source to this PN junction. If you don't apply it, the schematic diagram as you are seeing in this particular diagram. So the conduction and the valence band energy must bend as we go through the space charging. You see the conduction band. Now this is the particular schematic curve, and this is the valence band curve. So where the position of the conduction valence band with respect to the Fermi level is changing between P and, you can just say, P and N regions. Electrons in the conduction band of the N region see a potential barrier trying to move into the conduction band of the P region. The potential barrier is referred to as built-in potential barrier and is denoted as. So this particular region will call it as potential barrier, where the region where you don't find any type of charge carriers. So that is called built-in potential barriers at equilibrium position. This is at the equilibrium position. So the intrinsic Fermi level is equidistant. Now see, and this is the case when you don't apply any external field. The potential barrier means what? The region where you don't find the charge carriers. So we'll just say that no applied voltage across any PN junction. If you don't apply any voltage, external voltage to it, we just say that that particular region is a potential barrier. So we just talk about here at equilibrium. You can just see there is no connection here. We are not giving any type of any type of external field or external voltage to it. So what is actually the next? We'll move to the our next aspect now. What will happen? This is at equilibrium position. The previous figure, whatever we have seen, that is at equilibrium position. Now you can just see this diagram, forward bias. If I give the battery of voltage, the source is given to the p-type semiconductor. Here a p-type is given positive, this positive terminal. This big line is indicating the positive, and the small line indicates the negative terminal of the battery. So if the positive is connected to p-type semiconductor, and here the negative value is connected to n-type semiconductor, I just say that that is called the forward bias. Now when you apply, so further, see, if you don't understand, now just we'll go for this. Now when you apply some amount of voltage across this what you can say region, depletion region, what will happen? Then since always what will happen if the current flows through it? But in the most the current will flow through it. So what will happen when the current will flow? So now what will happen to that? The region, this particular region will be not depleted. Now the movement of electron will be there due to the application of the external battery or source of voltage we have applied. So what will happen? It will the electrons from the N junction and the holes from this particular majority charge carriers. So what will happen? They will break this potential barrier and they will move towards the N, and from here electrons will move to the P. So now this is called the forward bias, and which can be shown by this diagram. You can just see this diagram. So the electrostatic potential barrier at the junction is lowered, forward bias. Now what will happen if I go for reverse bias? See, reverse bias changing the polarities of the positive and the negative terminal. So if I change it, very less amount of voltage will flow, and that is what the reverse bias is all about. So here how this p-type and n-type look like when you apply some external field. You can see here, if I apply some external field for p-type, you can just see positive terminal. So for silicon imperi, see you can just see how the electrons are moving. Again I will repeat this. See the electron, see, you can just see this junction is formation of junction here. So here the negative charge is formed at the interface. Here you will find the positive charge at the interface. This is p-type and this is n-type. Now so we need not bother about this. See, you can just see how the electrons free to move and how they are moving here. Now, what is actually the depletion region? Again, for here, if you don't understand very clearly, so I just tell you what is actually the physics behind the depletion region. When n-type, n and p-type materials are placed in contact with each other, so the electron diffuses into the p-type region in order to equalize the Fermi level, and this loss of electrons from n-type material leaves the surface layer positively charged. So now we'll just say that is positively charged. Now similarly, the p-type material will have a negative charge surface layer. So thus an electric field is established. So when you have you got a positive charge and negative charge, definitely that is called electric field. So the electric field is established, which opposes the diffusion of current. So now, now what will be the size of the depletion? This can be calculated by this particular equation. We need not go for this expression now, right? So we know actually what is actually p-n junction is equal to. See, just now we just kind of discussed about the p-n junction. Here actually p-n junction is equal to so depletion region barrier to free flow of electron. So from p to n type that will act as a p-type semiconductor, n-type semiconductor, right? So here basically it forms a parallel plate capacitor. So this depletion region now we just call this as parallel plate capacitor. So this region, I'm talking about this region, right? So actually this p-n junction, this junction, when you talk about junction, that is called capacitor. You understood now. So what is this p-n junction is all about? Now, see, free forward bias, what will happen to the depletion region? The depletion region will shrink. It will become very small and the current is drag. It will drag through the barrier. See, the current will drag through the barrier. It has been shown here. See, you can just see. So it is what you can say. Again, I'm repeating this. See how the current is following when you give the electron, right? Now, so once the difficulty of getting through the depletion region has been overcome, the current can rise with the applied voltage. So this is actually contributing the Ohm's law. You can just see how this current is following with respect to the forward bias. So what will happen? In the reverse bias, the current finds more difficulty. What is actually reverse bias? I just now explained you. So here also p type n type. So you can say this is positive and this is negative. You see this reverse polarity, right? You can see the barrier here. The width of the barrier is small in the forward bias. Here the width of the barrier or the depletion region is more. Why? Because the polarity has been changed. Now what will happen? See, see. Here it is easy to travel, but it is very hard to travel. See, the charges are remaining here itself. Again, sir, little current, very little current flows because the barrier is too high. However, the increasing the voltage further, how you require a high electric field. If you see, here only plus and minus, very small. Now you require more amount of electric field to make the charges to move. So depletion eventually breaks down to the reverse current. Now see. Now you require very high current, high volt, high electric field. So then only your PN junction will be equal to the diode. So the diode, what is actually the meaning of diode? Diode is a two-terminal semiconducting device that allows the current to flow in one direction. So now this is what you can say. This is about the diode and so what is actually the meaning of diode? So diode is nothing but PN junction, right? We say PN junction diode. So p-type and n-type is combining. So that is called actually diode. So the diode is a two-terminal semiconducting device that allows the current to flow in a single direction. And how it is constructed? So p and n junction is connected together. Then there is a formation of p-n junction. What is the operation? What is the function that diode will do? No current flows because holes and electrons are moving in the wrong direction, right? So if you flip the diagram, see no current will flows across the junction. Across the junction there will be no current flows unless and until you will, what you do is that you give some battery to it, external force to it. So if you flip the battery around, the electrons are repelled by the negative terminals and the holes are repelled by the positive terminal, allowing the current to flow. Now this is actually about the what you can say PN junction diode and the diode function. So in the later class what we do is that in today's class again we just go for the now we just gone for the PN junction diode. So now we'll just move to the next important aspect of today's class, that is actually we need to understand what is actually thermistor. So in the last section we just I think that we got an idea. We talked about the extrinsic semiconductor, right? So extrinsic p-type and n-type semiconductor. So when you combine this p-type and n-type, then we will call p-n junction diode. In when you form a p-n junction, then definitely you will get an depletion. We talked about potential barrier and depletion region. So what is actually depletion region? We just talked about that. and what is actually, when you combine this p type and n type say extrinsic semiconductor, there is a formation of diode. And what is actually meaning of diode, what is the function of diode, so we just discuss about that. Now again, the important topic that we are going to learn here in today's session is what is actually thermistor. So here when you go for thermistor, thermistor, you just see thermistor. What is this thermistor? Resistors whose resistance changes with the temperature. So the thermistor is nothing but it is a resistor and this resistance is changing with respect to the temperature. So thermistor whose resistance changes with the temperature. So this is called actually resistive element, which is generally made up of the metal oxide. You can just say this type of thing, we'll call this as thermistors. And this is called, these are nothing but resistive elements, and these resistive elements is completely what you can say vary its characteristic. So generally metal oxides, it is made up of metal oxide, ceramic, manganese, containing manganese, cobalt, copper or nickel. So now thermally conductive glass, or it will be in the shape. See, this will tell us the shape of that particular thermistor. It is a glass bead or disc with two metal. You can see this is called beads, right? This is a glass. They may be glass or disc type, and this is the leads where you this is nothing but leads. Now the next important aspect. Now this is the most of the materials will exhibit two types of temperature coefficients. Here we just discuss here and now for this session, which is very important for our talk, is negative temperature coefficient. So thermistor exhibit negative temperature coefficients. Then the graphical representation. If you take the temperature, see when you talk about thermistor, we consider the temperature here in terms of Kelvin, right? So and x-axis, if you take the temperature, and y-axis you take it resistance. So why we are taking x-axis and y-axis? Why? Because we just studied that thermally sensitive resistor. Thermistor is thermally sensitive resistor. So therefore so how it is varying with respect to temperature, we want to see it. So by this graph you can just see this is exponential decay, where you'll find that practically we'll do in the practical lab also, we study the thermistor characteristic in the lab, right? Not only in the theory, there is a lab here there where you will practically you'll derive this type of graph, right? So now thermistor, what is the basic principle on thermistor? See, thermally sensitive resistor is known as thermistor, and the thermistor characteristic will change with respect to the temperature. That we are going to discuss in the lab period also. This is actually the symbol of the thermistor. You can just see this is a symbol of thermistor. So sorry. So we are all known that the resistor is an electrical component, and that is called a passive component, right? So in BWE, I think that you got an idea. Resistor is an passive component. It is electrical component. That what is actually resistor? What is actually resistor? Which will oppose the flow of current, right? So thermistor is a special type of resistor whose resistance varies more significantly with the temperature, and generally the resistance value is increasing with the temperature for the most metal, but for metals, right? So but the thermistor respond negatively. What is mean by negatively? That is, if the resistance of thermistor is decreasing, then the temperature value will increase. This is the main principle behind the thermistor. What's the basic principle? So the basic principle of thermistor is that the resistance of the thermistor, if it is decreasing, then the temperature, there will be definitely increase in the temperature. So as the resistance of thermistor depends upon the temperature, they can be connected in the electrical circuit to measure the temperature of a particular body. So here we'll just what is we talk about negative temperature, right? So first we'll talk about negative temperature coefficient. So many negative temperature coefficient thermistors are made from a pressed, just now we discussed. So disc or cast chip of semiconductors such as sintered metal oxides. Just now we just discussed, they work about raising the temperature of a semiconductor, increases the number of electrons to move to a certain extent. So now what is actually the uses of this negative temperature coefficient thermistor? They are used as a current limiter, and they are also used for digital thermostat and automobiles. In automobile engineering also there are few applications, right, of thermistors, right? So we use these negative temperature coefficient thermistors to monitor the temperature of the incubators, wherever newborn babies will be there. incubator, I think we got an idea. Newborn, particularly when you newborn, we can keep other things also, but we talk about incubators. So thermistor also commonly used in modern digital thermostats and to monitor the temperature of a battery packs while charging. So you can just monitor what will be the temperature of the battery while charging. So we regularly use the negative temperature coefficients in automotive application. There are different applications of the thermistor for automotive purpose also, and these thermistors are used in food handling and processing industries. So here now thermistors are nothing but they are also used throughout the consumer appliance industry, not only for the toaster, coffee makers, refrigerator, freezers. For all these things we'll use the thermistors where we require, see, in a refrigerator, when you talk about a refrigerator, where there is a part or a portion of the refrigerator where the temperature is very low, and there is a part of a temperature, there is a somewhat there will be change in the temperature, that enclosure, right? So there will be same block, but a different what you can say separations will be there. So in that separation also we make use of negative temperature coefficient thermistors. So we can regularly use these thermistors to 3D printers. Nowadays, not hot and happening is 3D printers. So in 3D printers also we'll use the thermistor. That is the reason that we just we are studying about the negative temperature coefficient resistance, which is resembling our semiconductors, right? So semiconductors also show this type of property. So negative temperature coefficient thermistor are used as resistance thermometers in low temperature measurements of the order. So what is that temperature? It can measure very low temperature, even 10 Kelvin. For 10 Kelvin measurements, we can use the negative temperature coefficient thermistors. So now this is the very huge application. Due to these huge applications, we just studied about the thermistor. So now I think that you got a very clear idea. So in today's class, we just discussed, we have started with the Fermi level. What is actually Fermi level? Where we have used this carrier concentration of the electrons in the conduction band. There we have used the Fermi function. What is actually Fermi function, and what is this Fermi function is equal to mathematically? So we just discussed, and what is the importance of the Fermi function with respect to the temperature. We discussed about the Fermi function and how this Fermi function is depending on the temperature, and the later section we discuss what is actually the extrinsic semiconductor. So when you talk about extrinsic semiconductor, p-type and n-type extrinsic semiconductor, and the p-type and n-type extrinsic semiconductor, when you join this, so definitely you'll get a diode. And what is the function of the diode also we just studied here. And in that what you can say p-n junction, when you don't apply some external electric field, so there is a depletion region is formed, potential barrier is formed. So the potential barrier and depletion region, how that charge will flow for forward bias and also reverse bias, we discuss in today's class. And then we just started with the thermistor and studied what is actually the meaning of thermistor, and we studied about negative temperature coefficient. Particularly, there is a positive temperature coefficient is also there, but we have given our due importance to the negative temperature coefficient. What is actually thermistor? What is negative temperature coefficient of thermistor? And what is the basic principle on which the thermistor is working? And what are the different applications? Why we have studied about thermistor? So just now we just had a very huge applications of the negative temperature coefficients of thermistor. So with this, we'll just end our today's class. So we'll again meet in the next class for the last topic of your chapter 1, unit 2.